So we've talked a lot about strain being a tensor so far, and we've talked about vectors being kind of degenerate level of tensor and so forth. Well, now it's finally time that we get into a little bit more detail about how we can define what a tensor is. And in order to do this, we need to talk a little bit about coordinate transformations. Now, when I say a coordinate transformation, I mean if we can imagine us having a coordinate system, maybe our typical x and y coordinate system that we have, and we can go 3 dimensions if we want. Our z-axis here. We have a coordinate system, and we have another coordinate system at that point that's rotated with respect to the original coordinate system. So maybe this is a capital X coordinate system and a capital Y coordinate system over here. So we can imagine having 2 coordinate systems at the same point, and if we have a vector, we can write components of that vector in either coordinate system. Now, to make things easier at first, we're going to consider a plane transformation. What I mean by that is the little z and the capital Z coordinate systems are pointing in the same direction, and it's just a rotation about the z-axis in the plane that's formed by the x and the y-axes, or the capital X and capital Y. So to start us off, we're going to take a look at a vector that's in this coordinate system, and we've talked about displacement vectors already, so let's just say that this vector we're going to call u. We can think of it as a displacement vector if you want, but it doesn't have to be a displacement vector. It's just whatever convenient that we want to look at, just some vector that we have right here. Now we know that that vector exists without regard to any coordinate system. It has a certain magnitude and direction in an overall global sense. But we can write that vector with components in either coordinate system. So as we had talked about at the very beginning of the semester, we have unit basis vectors, and we're going to call this e hat 1 and e hat 2 in the little x and y system, and we can call the unit basis vectors in the capital X and Y system, let's just call it capital E hat 1 and capital E hat 2. And these are orthonormal unit basis vectors. We don't have to use orthonormal unit basis vectors, but that's usually reserved for classes where you have a little bit more going on than what we're going to have in our class. Curvilinear coordinates, distortions that are substantial, and then you have more ways to write things. You just have to be a little bit careful. But for us, we're going to stick to our unit orthonormal basis vectors. Right, so we can write this vector u that I have right here either in terms of the little x and y coordinate system, and this vector u would have components u1, u2, and u3, in the little xyz system, or we could have just as easily written that vector u in terms of components in the capital xyz system. Now, to differentiate these components, I'm going to call it with a star. So I have u1 star e hat 1, u2 star capital E hat 2, and u3 star capital E hat 3, and then that would be in the capital X, Y, and Z system. It's the same vector, but it has different component representations in the different systems. Now we're eventually going to be able to figure out how to write the u1 U2, U3 components in terms of the U1 star, U2 star, and U3 star components, and vice versa. The key to this is that we know that we can write the unit basis vectors in terms of each other. So for example, suppose we have a rotation this way of theta from our original x and y system. Then capital E hat 1 would be composed of some movement in the x direction, which would be cosine theta. So we're breaking this up into components. So it would be cosine theta times little e hat 1 plus sine theta little e hat 2 plus, well, in this case, 0 e hat 3. So if I want to get this way, I'm going to first have to go over this way and then up. Right? And in a similar way, if we want to define capital E hat 2, well, we would first go up the y-axis, and then we would go this way in the negative x direction. So we would have a minus sine theta E hat 1 plus cosine theta E hat 2, and then a 0 E hat 3. And for our plane transformation, we would have 0 E hat 1 plus 0 E hat 2 plus 1 E hat 3 to give us capital E3, since they are coincident. Now when we do this, we still have to be careful that the capital E hat are unit basis vectors. Since what we have here is a linear combination, it's going to be convenient for us to think of this in a matrix format. So we have these unit basis vectors equal to a matrix full of these coefficients times our original unit basis vectors. Now in general, we would have something that looks very similar. And some books use different symbols for this. I'm going to use the symbol m, but we have a coefficient, a matrix of these coefficients, m11, m12, m13, and then so forth as we transform from one coordinate system to another. And this matrix is called a transformation matrix. There are some properties of this transformation matrix. Remember, we set our basis vectors up to be unit basis vectors. So if we did capital E hat 1 dotted with capital E hat 1, okay, so we're taking this row and dotting it with itself, we would get m11 squared plus m12 squared plus m13 squared. And since this is parallel, cosine of 0 degrees is 1 and the magnitudes are 1. So this is equal to 1. It's basically our direction cosine relationship again. And likewise, we can do the same thing for E hat 2, except we use the next row. Now it is important to keep in mind that this transformation matrix is not symmetric. As we can see, when we're up here and this entry is sine theta and this one is minus sine theta, for example. There are some interesting properties, though. The inverse of the transformation matrix is equal to the transformation matrix transposed. So if we have this matrix Mij, the transpose of that matrix is equal to the inverse of that matrix. We can write Mij, the transpose of that matrix, we can write that as the components Mji. Now we could just as easily do things the other way around. We could write the little e hat I unit basis vectors in terms of the capital E hat I. And let me go ahead and write those down. So if I wanted to get to little e hat 1, and this is the angle theta, I would have to go cosine theta in the capital E hat 1 direction, and then since I need to go this way, let me sketch that in with a different color. We'll be going a little bit this way and a little bit this way. Notice that's in the negative E hat 2 direction. So I'd have a minus sine theta capital E hat 2. And for our plane rotation, we'd have a 0 E hat 3. And likewise, very similar to what we've done before, but now we have a plus sine theta E hat 1 plus cosine theta capital E hat 2, and then again a 0 capital E hat 3, and then the last one is easy, 0 capital E hat 1 plus 0 capital E hat 2 plus 1 capital E hat 3. And we can construct the matrix as we did before, this way the other way around. And it makes sense that it's the transpose, or it makes sense at least that it's the inverse, and we can see that when we have this relationship written this way, it's also the inverse. So we can do things one of two ways. We can say that the capital E hat k unit basis vectors are equal to Mik, the transformation matrix, times the E hat I unit basis vectors. Or we can do it the other way around. The little E hat I are equal to the inverse of Mik capital E hat k, which are equal to the transpose of Mik E hat k, which is equal to Mki E hat k. So these are all the same thing. So we can write the new, if we want, in terms of the old, or we can write the old in terms of the new by using these different ways that we've written this transformation matrix. Now, we've talked a lot about final configurations and initial configurations. Okay, now these coordinate systems don't have anything to do with that at this moment. We're taking a look at one configuration, say our original configuration, and instead of having our coordinate system lined up with what we think of the traditional XYZ coordinate axes, we're now rotating to a new set of axes in that particular configuration. So keep that in mind as we're talking about this rotation. So with that in mind, let's take a look again at our vector u. Once again, we can write u in terms of either the little e hat system or the capital E hat system, and we get those different components. Little u1, little 2, little u3, or u1 star, u2 star, u3 star. And we've seen how we can write little e hat 1 in terms of capital E hat 1. So let's write this out to the side. Little e hat 1 would be equal to m11 capital E hat 1 plus m21 capital E hat 2 plus little m31 capital E hat 3. Now, this is the transpose of the matrix as we had originally written it, but we saw how that worked out just on the previous page. Have to be really careful when I write these down this way. Okay, so that's what it is in general. So if I want, I can go back up to my top line, and I can say that this vector u is equal to the component u1 times a little e hat 1, which is m11 capital E hat 1 plus m21 capital E hat 2 plus m31 capital E hat 3. Now we could just write down an equation, but I want you to see where all these terms come from in the equation. So that's why we're taking the kind of the long way through things. Once we get really going with our index notation, I'll expect that things make a little bit more sense. And if they don't, then come back and take a look at this again. But I'm going to go ahead and write down these next two lines. Basically, I'm just copying down what I have from a substitution. And then the last line, the U3, we have the M13, the M23, and the M33 times those respective capital E unit basis vectors. Now, instead of writing these this way, I'm going to do a little bit of manipulation, and I want to group all the capital E hat terms. Okay, so when I do that, I'm going to have a U1 times M11 plus a U2 M12 plus a U3 M13, and then I have the capital E hat 1. And likewise, as I do this grouping, I'll kind of go down this next column and then this next column, but I'm writing them out now as rows. U1, M21, U2, M22, U3, M23 times capital E hat 2, and then again U1 M31 plus u2 m32 plus u3 m33 times a capital E hat 3. Now, we did say that this was equal to these components right here. So that's all equal to u1 star capital E hat 1 plus u2 star capital E hat 2 plus u3 star capital E hat 3. And so what that means is these respective coefficients in terms of these capital E unit basis vectors are equal to one another. So u1 star is equal to, we'll write it out, u1 m11 plus u2 m12 plus u3 m13, and so forth. I won't write all three of those out, but you can see very easily where each one of these would come from. Now, in general then, you see how we have a repeated index on the second subscript. We can say, and then this subscript here would be like a free index. The only thing that would change between these three lines would be, it would be 2 for this row and then 3 for that row. So we can say in general terms that ui star, where I could be 1, 2, or 3, the free index, is equal to mij uj. So over here is the new components, that's the new coordinate system. We have the transformation matrix, and then this uj is the old system. So that's really pretty straightforward, but the one thing we do have to be careful about is the way in which our transformation matrix is defined. So here across the top would be like my old system, and here along the bottom would be my new system that's rotated with respect to the old one. And then my coefficients, my transformation matrix, would go this way. Here would be my M11, my M12, my M13, and so forth. So I would first, the way I would find it is, for example, again, the capital E hat 1 would be equal to this transformation coefficient M11 times little e hat 1 plus M12 little e hat 2 plus M13 little e hat 3. Okay. If we write it the other way around, now we've got the transpose, and things just need to be treated very carefully. Okay. So this is how we're going to find that. And there's a table in our book in chapter 1 that effectively shows the same thing as what I've just written down. Okay, so let's write it down again. If I want the components of any vector in a new coordinate system, those new components would be equal to the transformation matrix. I'm calling it mij. Other books call it different things. Times the original components, uj, where we have an implied summation over j. And now we can finally define what a tensor is. So a vector, we've said, is a first-order tensor. first order tensors transform by the application of one transformation matrix. And when I say transform, I mean for a coordinate rotation. So we have one transformation matrix. We have UI star is equal to Mij uj. A second order tensor transforms through the application of two transformation matrices. Okay, so for example, if I want the components of a second order tensor in a new coordinate system, say components Wij star, then I would have the transformation matrix Mik Mjl times the original components Wkl. And you see the free indices. Free indices are I and j, and they appear in these two terms. And the dummy indices, k and l, appear in these two terms. Okay, so a second order tensor transforms by the application of two transformation matrices, and we can have a third order tensor and a fourth order tensor and a fifth order tensor and whatnot. We can get up to an nth order tensor. I'll use a similar type of notation. An nth order tensor can be represented by components that have n subscripts. So P1, P2, whatever, all the way out to Pn. Like if it was a fifth order tensor, that would be T, I, J, K, L, M. Right. So these new components in the new coordinate system, that with the star, would be equal to transformation matrix M. I'm going to call this P1, Q1, another one, P2, Q2, and so forth and so on, all the way out to M, P sub n, Q sub n, times the original components without the star, Q1, Q2, all the way out to Qn. So an nth order tensor transforms by the application of n transformation matrices. And that is a commonly accepted definition of nth order tensors. If that transformation holds, then it is a tensor. Now, at this point, I want to point out that the representation of tensors that we're often talking about end up looking like matrices. All tensors can be represented in a matrix of components, but not all matrices are tensors. A tensor is something that has to obey this special transformation rule based on these transformation matrices. Now, in a way, this is a useful definition, because if we know the components of a tensor in one coordinate system, and if we know the other coordinate system we're going to, we can definitely compute the new components in the new coordinate system. But just like we've seen with vectors, the vector exists without regard to its coordinate system. The vector is just a creature on its own. It doesn't know what coordinate system you're using to represent it in. Likewise, tensors are, you can think of them as things, creatures that live on their own, and they exist with certain properties without regard to the coordinate system in which you've chosen to represent them. So there is another way that we can define tensors, and it depends on the way that it operates on something. So let's talk about that. Okay, so that coordinate-free type definition, we can say that a tensor is a linear operator that transforms one tensor into another tensor, and if we want to be more precise, we can talk about the spaces on which it transforms and so forth. For us right now, this is a perfectly fine definition. We've talked about what linear operators mean previously, and so we can give an example of what I mean here. So if I have the strain tensor and I have it operating on a unit normal vector like we've done before, we've seen how we can represent that in components. We have a 3 by 3. Here we have a vector, and what do we get out of it? We get another vector. Okay, so in this case, the second order tensor operating on a first order tensor, or vector, produces a first order tensor. Another example, if we have the elasticity tensor, we haven't talked about that yet, but we will, and if it operates on the strain tensor, so this is a fourth order tensor, fourth order tensor operating on a second order tensor will give us the stress tensor, which is a second order tensor. Okay, and you notice in these two examples I haven't tied myself down to any particular coordinate system. Coordinate systems are great, you need them if you're going to work particular problems, but finding the essential ideas behind a concept, if you can do that in a coordinate-free approach, then you have a much more general approach than if you're tied to any particular coordinate system. Alright, so there's one thing left to do in this lecture, and that is to see whether or not the strain tensor, which we've been calling it the strain tensor for so long, to see whether or not it really is a tensor. Alright, so we're going to take a look first at two coordinate systems. We're going to have, instead of little xyz and capital xyz, we're going to have two coordinate systems, the x sub I coordinate system and the y sub I coordinate system. And we know that we can characterize the difference in the square of the length from one coordinate system to the other, back when we first started talking about strain, as ds squared minus d regular s squared equal to 2 epsilon ij dxi dxj. Okay, now we're not using the unit normals this time. We're using the actual distance in between those 2 points. Now if we look at the left-hand side is a scalar, and it is completely invariant to any kind of coordinate system we want to represent our particular tensors and vectors in. So we could have just as easily said that the difference between these two square of the lengths terms is equal to some other coordinate system tensor components in the other coordinate system dy m dy n. So capital E I'm using here is the strain tensor in the y sub I system. Now dxi is itself a little vector, and we know how to transform that into other components. We can say dxi is the transformation matrix m sub I dy sub m, where I'm using m as a dummy index. And then by the same reasoning I can see dx sub j is equal to transformation matrix m sub nj dy sub n. Okay, so if I set these two things equal to each other, the 2's will cancel out. I can have capital E m n dy m dy n equal to epsilon ij dxi dxj and if I write that one more time, these transformation matrices, let me write them out front. M subscript mi, M subscript nj, epsilon ij, dym, dyn, and since I have this equal to that, I can group them together on one side if I want. And collect the common terms outside of the bracket. And that would be equal to 0. Now neither one of these can be the 0 vector, so that leaves this to be 0 inside the parentheses. And if this is 0 inside the parentheses, then the new components are equal to 2 transformation matrices times the old components. So we've just shown by the definition of a second order tensor, using the component definition, that this is a second order tensor. Now in terms of our other coordinate-free representation, we can kind of think through that. We have the strain tensor that is operating on a vector. Okay, it can either be our unit vector, or as we've just been using, some vector that represents the distance between 2 points, and that results in a vector. And so we have then our second order tensor, and this then would have a length. So this is unitless. This has some units of length. And then we do that resulting vector times that same vector again. We have the length dotted with a length, and then we end up with a length squared term, which is what we get when we have the ds squared minus ds squared. And again, if we want to think about this visually, if we have our bar, I'm going to draw it horizontally this time, we may start off that bar having a sphere in it. I'm going to show it as a circle in 2 dimensions. And all these line segments going through that sphere. And when we distort it, then all these line segments cause that sphere to distort into an ellipse. Or in 3D we call that an ellipsoid. In particular, we can call that the strain ellipsoid. Now we're ready to go through and talk about principal strains and the eigenvalue problem. So we'll do that in the next lecture.